Hello and welcome to Pep Talk with me, Mr. Pepperell. Today, I'm going down a gold mine to see if I can strike it rich. But just where did gold and all the other chemical elements come from? By the end of this video, you should be able to tell me what chemical elements are formed inside a star, what chemical elements are formed in a supernova, and why does the Earth contain heavy elements?
So you'll hopefully remember from our previous work that the temperature inside a star such as our sun is great enough that the process of nuclear fusion can take place and the light hydrogen nuclei can begin to fuse together to form the heavier helium nuclei via a number of steps, okay? And remember, it's the energy released by this process that stops our star collapsing due to its own gravity, okay? But what's going to happen when that hydrogen has run out and there's no more fuel for nuclear fusion to take place and there's no more outward pressure? Well, when this happens, what happens is gravity wins and the star will start to collapse, okay? So what we've got here is a shell of hydrogen that has been fusing together to form the helium, and we've got a helium core in the middle. But when there's not enough hydrogen left to continue the fusion process, there's no outward energy anymore and the star begins to collapse, and the helium core here starts to collapse on itself, but as it collapses it starts to get hotter and hotter, and eventually it will get hot enough that the helium can start to fuse together. Remember, the heat gives the nuclei enough kinetic energy to overcome the electrostatic repulsion of each other, and when it gets hot enough the helium will actually start to fuse together. So what we then get is the original hydrogen shell. We've got a helium shell where we're now producing energy and the star can start a new stage in its life. The helium is fusing together to produce energy which can battle the gravity and the star becomes stable again for a bit, okay? But of course eventually the helium's going to run out and the core will start to collapse again, but as it starts to collapse it's going to start to heat up and we start to get more and more fusion reactions taking place. So here we can see that process in a bit more detail. What we've got is the helium that was originally produced, remember, by hydrogen nuclei fusing together. As the star starts to collapse, the core starts to heat up even more, and eventually gets hot enough, these particles gain enough energy to overcome the electrostatic repulsion between them, and they will fuse together eventually to form beryllium. And eventually when all the helium runs out, what happens is fusion stops. The star starts to collapse again. As it collapses, the core starts to heat up, and eventually the remaining helium can start to fuse with that beryllium to form carbon. So you can see that, each time a nuclear fusion event occurs, energy is released, and this firstly causes the star to shine. Obviously that's where we've got this energy being released here, okay? But secondly, it balances out the force of gravity. But each time the supply of an element, hydrogen to start with and then helium, each time the supply of an element is exhausted, the force of gravity wins. The star's core begins to collapse and it gets hotter in the process, and it's this extra heat that allows the new fusion reactions that produce the beryllium and then produce the carbon to start forming larger and larger nuclei. And what eventually we start to get is something that looks a bit like this, okay? So we've got our original hydrogen in the shell around the outside. When there wasn't enough of that to continue fusion, the core started to collapse and the helium started to fuse, and we get a shell of helium. But when that started to run out, the core collapsed again, and eventually it heated up and the helium started to fuse eventually to form carbon. Then the carbon ran out and the core collapsed to form neon, and the neon ran out and the core collapsed oxygen and silicon, and we start getting larger and larger nuclei forming. But do you know what? This process can't go on forever. After many repeated steps of the star starting to collapse and the core heating up and starting to fuse heavier nuclei together, what happens is the nuclei will start to form the element number 26 on the periodic table, which is iron in the middle there. And when it gets to iron, when the fusion process gets up to iron, that's when the whole thing just grinds to a halt. And this is because the amount of energy you'd actually need to fuse the nuclei of iron together is too great, okay? Doesn't matter how hot the star gets, it's not going to be enough to start fusing iron into heavier elements than iron, okay? So this is when nuclear fusion stops, and when fusion stops, of course, there's no more energy being released, and when that energy stops being released, basically the forces in the star are no longer balanced like they once were, and gravity has finally won the battle of the star, okay? There's no more outward pressure anymore. Gravity now starts to collapse the whole core down, and the star starts to collapse for one final time. So as this happens, the collapsing outer layers of the star that we've got here, actually, as they collapse inwards, bounce off the core and they rebound back outwards at about 40 billion meters per second. That's about 10% of the speed of light. And that's a result of all the gravitational potential energy that was locked up in this gas. As it's dropping in towards the core, this gravitational potential energy is being released, and that results in a massive shock wave rattling back out from the centre of the star. And what that shock wave causes is a cataclysmic explosion that we call a supernova. Now, the energy released during a supernova is so immense that for a very brief time, perhaps a couple of days, a supernova can actually outshine an entire galaxy of millions of stars. So here, look, we've got a single star down here which has just gone supernova, and it is brighter than this entire galaxy of stars, which is obviously it's part of that galaxy, but it's brighter than all of those stars put together. And we can see over here in this another image, this is quite a famous image from a supernova that happened in 1987. We've got a single star here. Look, this is the day before it went supernova. The core's probably just about to collapse there. Okay, the fuel's run out, it's fused into iron, there's no more energy to be released, and all of a sudden the star has gone supernova there, and you can see how much brighter that is on the day that that star went supernova. It's also this enormous burst of energy that is responsible for the formation of all the elements heavier than iron, okay? Because for a brief moment, as this shockwave goes back out through this cloud of gas surrounding the collapsed core, okay, all the nuclei there, the heavy nuclei, are combined due to the immense heat caused by the shockwave passing through the cloud. It condenses this gas of cloud so much, the heat is so amazing that it can actually cause all the nuclei to fuse together to form the heavier nuclei that we know are above iron all the way up to uranium, and they're all formed in a brief moment as this shockwave passes through this cloud of gas, and the shockwave continues and it just scatters all of these newly formed heavy elements all across the cosmos, okay? And from there, these elements then form vast nebulae that will eventually begin to collapse under their own gravity and form new stars and planets. So here we've got some images of supernova remnants. This is the big clouds of gas that have been left in space, the big nebulae that have been left as a result of supernova explosions. And you can see the shock wave that's coming out through these things, and in all these pictures there are actually the new elements being formed and scattered across space. In fact, all the heavy elements that our current planet, Earth, is composed of were formed in a supernova. All the things that we can see here that make up the crust and the core of the Earth were all formed in a supernova. They wouldn't exist if a star, just like this one here, hadn't gone supernova. Now, the heaviest element found on our Earth is uranium, okay, and that could only possibly have been formed by a dying star when it exploded, and that shock wave caused the immense heat that caused the nuclei to fuse together to form these heavy elements. And in fact, pretty much all the atoms that your body is made up of were formed at the heart of a star as a star collapsed, okay, and then exploded outward at about 10% of the speed of light, outshining millions of other stars in its galaxy just for a brief moment. So in a way, it is possible to say that, yeah, we are all actually made of star stuff. So let's just recap this whole process from start to finish. We started with a giant molecular cloud of gas and dust in space that started to collapse under its own gravity and heating up as it did so to form a protostar. And eventually that protostar moved into its main sequence there, and during this time it was fusing hydrogen together to produce helium. And as that hydrogen ran out, okay, the core started to contract and heat up even more, and the outside layers started to cool, forming a red giant that we talked about. But eventually the core got so warm that it could start to fuse the helium together to make the heavier elements of beryllium, and eventually as the core collapsed, when the helium supply ran out, it started to fuse the nuclei together to make heavier and heavier nuclei until we reached the stage that we were fusing nuclei together to form iron. And you can't fuse the iron together, no energy gets released by that, so at that point the star started to completely collapse and went supernova, and we formed these giant nebulae which eventually will start to contract into new stars, and the whole thing is just a cyclic process and goes round and round again. But of course it's really important because this is the process that produces all the elements in our universe.
So that's everything we need to know about a process which is actually called nucleosynthesis, the synthesis of new heavier nuclei. And as the late great Carl Sagan said, we are indeed all made of star stuff, because pretty much every atom in your body heavier than hydrogen, all the atoms our planet are made out of, and indeed the gold down the gold mine at the beginning of this video, were all forged inside the heart of a dying star as its core collapsed and heated up, and the shockwave blew out with 10% of the speed of light, forging all the elements which make up you today. Any problems with that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.